Hi there. In this video, I'm going to take a look at debugging MIDI serial data on an oscilloscope. So what's some of the equipment we'll need to look at the MIDI serial data on the oscilloscope? Well, starting off, something that outputs MIDI data, and more than likely this is going to be a DIY controller that you've made, or possibly something from a kit, or maybe you're just trying to troubleshoot a commercially available product. Now, I did not make this keyboard. Obviously, this is a commercial product, but for today's video, we're just going to pretend this might be some type of MIDI controller that I have made, with some type of microprocessor inside that's sending out the MIDI data. And that could be an Arduino, that could be, PIC, that could be all kinds of different microcontrollers inside, even dedicated MIDI controllers. So you'll need some type of device that outputs MIDI information. Now, the best way to look at that on an oscilloscope is going to be through this little module here. This is by a company called Toy Makers. And this module is called the MIDI in Me. And basically this is just the circuitry with an opto isolator on it. The MIDI specification, if you look up the hardware MIDI specification, that is actually how the receiving device should look at the MIDI protocol. So it's basically a 5 milliamp current loop. So in order for that to work, the MIDI data is streamed out just one pin on the cable of a MIDI device, goes through the opto isolator, and then basically comes back to that same MIDI device. So it makes a loop. The opto isolator converts that to a voltage, and that's how your other receiving device interprets that data. So we're picking that off on the other side of the opto isolator, on the isolated side of it, to actually read the data onto the oscilloscope. So this is a handy little module. It's super cheap. I'll have a link to it in the video description. I highly recommend it. Now, today I also have a bus pirate hooked up to the MIDI in Me module, and then we're probing the MIDI in Me module right at that connection. So this is connected to ground and the data output. And then that is also at the same time being fed into a MIDI bus pirate. And you don't necessarily have to use this. A lot of people would say that's being redundant because we're already using a device that decodes MIDI serial data, which is true. This is just for me to double check. I can see it pop up on my computer, and I can also watch it on the oscilloscope. But the other thing is this MIDI in Me module seems to work better if it has a load attached to it. I've tried hooking up the oscilloscope just to the output of this, and the waveform isn't that great. There's a lot of noise, so for whatever reason, having an actual load hooked up to it and then probing it with the oscilloscope seems to work a lot better. And then also, the various cables, so a MIDI cable, power cable going to my MIDI keyboard. So a few miscellaneous cables, obviously the oscilloscope probe, and then obviously the oscilloscope. So it will help if your oscilloscope has a one-shot mode. Now, I do have an old analog oscilloscope, but it does not have any kind of one-shot mode or digital storage. If yours does, you can still kind of do this. But this is gonna be a lot easier with a more modern digital scope, especially one that also has serial or RS-232 triggering, which the one we're using today does. And then also decoding, serial decoding. Now we'll take a look at how to set up the oscilloscope. The one I'll be using today is the Regal DS1054Z. Now this one does have all of the options enabled on it. So that will help with both the triggering and the decoding that we're going to be doing today. So if we take a look here, I'm just using one channel. We're on DC coupling. The probe is set to 10 times. And that's pretty much all we need on the channel menu. The next thing we'll do to kind of make life easier is go over to the trigger menu. So now we see a whole bunch of options that come up when you press trigger menu. You'll notice the type here when we go into this. You know, most of the time, depending on what you're doing, you might use edge triggering. But if your oscilloscope has either serial or RS-232 decoding, that's what we're going to need. And so we can close that out. Our source is channel 1. Our polarity is set up to where high basically is the status we're at right now, and as data comes in, it'll be going negative. Win is at the start bit, so we'll take a look at that here in a minute. But we also then need a user baud rate, because MIDI info, the baud rate it uses is 31.25 kilobits, and so per second, that is. And so that's not standard in any other real communication protocols. So you'll need to go to this user baud rate and then dial in 31,250, and that's the MIDI communication baud rate. And then from there, the next thing we'll need to make life easier is if you go into the math menu, at least on this oscilloscope, and then we have, that's where the decoding options are. So we'll go into there, and you'll see I already have the decoding set up. So, you know, on this oscilloscope with all these options, there's parallel, I2C, and SPI. So we're going to be using the serial or RS-232. So that's good. Decoding is turned on. Channel 1 is where we're going to be decoding from. The baud rate, once again, 31,250. And I think that's all we need. Our polarity is already set. Oh, and also least significant bit first. That's also in the MIDI spec, and we'll look at that a little bit later. And it is going to be, the data is in a 8 byte word, and also just 1 stop bit, no parity. And I think that's all we got. And for right now on the decoding, I'll leave it, I have it in hex mode. There's different things, so hex, decimal, binary, ASCII, and line. We'll leave it in hex right now because that's usually how we refer to transmitted messages in MIDI, but we'll take a look at binary also. The position is just where it's going to read out on the screen, so we'll deal with that in a little bit. But that's pretty much all we need right now to get an oscilloscope set up to do this. Now, this is obviously the menus and setting for this particular model of oscilloscope. But hopefully, if you're using a different model, you'll be able to find in the manual if you do have those options and how to set those up. So real quick before we look at the actual data on the oscilloscope, we'll take a quick look at 3 different web pages that I found. Now there's many more than this, but these are the 3 that I found that kind of helped me the most when looking at MIDI data. So the first is a personal site at Kent University, and it's just titled The MIDI Physical Layer. And basically this just goes through some of the differences and similarities between RS-232 data and the MIDI protocol. It also shows a little bit about hardware hooking this up. It shows that opto isolator, which is part of the module that comes with the MIDI in-me from toy makers that I mentioned earlier, and talks about some of the MIDI cabling and wiring. The biggest help you're going to find usually comes from MIDI.org. This is the MIDI association that defined the standards and updates them as needed. So I found this table here under specs, MIDI reference tables, and then the summary of the MIDI messages. Now, most MIDI data that you're going to find in the references is going to be written in hex or hexadecimal data. Luckily, this is actually in binary because, see, on the oscilloscope, we're going to be seeing the actual ones and zeros or highs and lows on the oscilloscope, and this is written in binary, so that's going to be a little easier to decode. Now the oscilloscope will do it for us, but as far as cross-referencing to make sure everything's coming out correctly, this will be a little easier. There's many different types. We have channel voice messages, channel mode messages, and as you can see, quite a few, pardon me, more system real-time messages. But another website that I find helpful is at this electronics.dit.ie. And this just kind of breaks down how MIDI messages are both transmitted and measured. So once again, it talks about our kilobits per second. The messages are in 10-byte words because even though it is, 10-bit words, even though it's an 8-byte message, it also has this start bit and stop bit. So the 2 bits on with the 8 equals a 10-bit word from the 8 bits in the single byte. And then 3 words or bytes are going to come across because of the data rate. They're going to be 320 microseconds each, or for this whole transmission would be 960 microseconds. So it gives you the frequency and formula if you want to be able to calculate that yourself. We're just going to be looking at channel voice messages. You can see there's mode messages, system messages like we saw on this other page here. And then it shows some of the variables as they change. But today we're just going to look at channel voice messages. Let's go ahead and take a look at what we get when we just go ahead and try to capture some data on the oscilloscope. I'm going to go ahead and put this into single shot mode, and I'm going to hit basically middle C. I'm going to hit it fairly hard so we can see if it comes in at maximum velocity. And then we'll take a look at what this looks like on the oscilloscope. All right, so on the oscilloscope here, we do have our MIDI message displayed here. So as we kind of looked earlier, this is 3 different words, 10 bits a piece with 8 bits for the byte on each one. So when we decode this with the oscilloscope, as you can see, we triggered it because we had the trigger set up, and we also decoded it all at the same time. And this decoded into hex because that's how we have it set up right now in the menu. So each one of these green squares is each one of our byte messages, both with the start bit and stop bit. So right before the green box, it goes down, and that is our start bit. And right after the green box here, it goes up, and that is our stop bit. And as you can see, we always start out that way. As we looked on the little diagram earlier, it always has the start bit, which for this logic level and the way it's displayed goes down, and it always ends up. So the 9, 0, that represents a note on message. 3C, once again, these numbers are all in hex or hexadecimal. 3C is the note number. So I have this set up to middle C, which is usually C4. Now that's another thing. Different manufacturers have middle C sometimes set up to different numbers. But most of the time, 3C is going to equate to MIDI pardon me, note number C4, C being the musical note, and then 7F, we got that value because I played it as loud as possible. So in hex, that's going to be the loudest or most velocity that we can get. So once again, it's note on, the note number, and the velocity. So we got 903C 7F. I'm going to go ahead and put this back into single shot mode. And well, actually, I'm going to put it into run real quick. I'm going to hold down on the same note we hit, so middle C. I'm going to put this back into single shot mode. I'm going to let off, because see, there's two different notes, two different pieces of information that are sent out. Down is note on, and up is note off. So when I let up, all right, so now we have 80, 3C, 1F. So 80 corresponds in hex to note off. We're still on 3C because I still was letting go of the middle C, C4 in the note range. And 1F because now it was a slightly different velocity. So this keyboard does send out note off velocity. So basically how easy or quick you let up on the key depending on which one. And also a note, this keyboard sends out a MIDI note off message. Some will just send out a MIDI on message with a velocity of 0. Now that gets into what's called running status mode. We're not really going to cover that today, but if you look up MIDI running status mode, you'll find out some more about that, and I may touch on it a little bit later. But once again here, we're looking at this MIDI hex data. Now, I don't know about you, but without having a table to go off of right next to me, this is going to be a little hard to decode, especially if we're having some problems. So what we can do is go into the decode menu, and we will change this from hex. Well, we can do a few things. We can actually go to decimal, and so we can actually see the decimal values that we're sending. But that, once again, doesn't do us a whole lot of good right now. But if we go to binary, do it that way, and I'm going to go ahead and set this back over to single shot mode, and I'm going to go ahead and hit that middle C, the note on again. So now what we have are the same, in fact, I'll show you the same message we had earlier in hex. So it's still the 903C 7F. But once we go into binary, we'll see a little bit easier on decoding this with our up and down, our high and low values. So in this first word, 10-bit word, like I say, we have a start bit and a stop bit. But in between here, we have different values. So the first nibble of this byte is 1001. Now then, that is indicating note on. Now the second nibble of that byte is all zeros. That's because that is the channel indicator. So we are on channel 1, which, you know, because it starts counting at 0, that's where that comes from. Our second word or byte is the binary representation of the MIDI note number. And finally, we have the value of the velocity. So you remember it was the loudest we could get it, which happened to be the 7F in hex. So when you convert that to binary, this is what you see. Another thing with these MIDI messages, they are transmitted with the least significant bit first for each one of the bytes or words. So it's almost the opposite or reverse. So basically this 0, in fact, these 4 zeros actually come down the line. So if we start with, this is time, so the message started here and it finished here. So time starts on the left and progresses towards the right. So the 4 zeros are actually represented right here. These are low on the screen, and so after our start bit, which is also low, then if we were to count over, now the graticals on this won't line up to our baud rate. At least I couldn't figure out a way to do that, but we can get the cursors out, or if you want to do that on your own and actually measure, and it'll show that. And then, so this 1 then is this high bit, and we have 2 zeros. So there's the 2 zeros right here, this spot where it goes down. Then we have the 1 again, which is actually right here, plus our stop bit. And then that is also high right there. And then the next message starts. So we always start with a low for the start bit. Least significant first, so we have 2 zeros, so we have 2 marked positions that are down, and then we have 2 high, and then 2 more high, so that's 4 ones in a row. Then we end with 2 zeros, so if you were to count that, those would be 2 lows, and then our stop byte, which is always high. And then same with the velocity number here too. So it's gonna start with a low right here. So this little thing here on the first leading edge of that box, that's our low, our start bit. We have 7 ones, so that's why this is high right here for this whole time. We have a 0 at the very end of the 8 bits. So that's that, and then it ends again, once again, with a status low or off, which in this case, the way we're looking at this, happens to be at the top of our range here. So we looked at the MIDI no on and off message. Now let's take a look at MIDI control change, or sometimes continuous controller is how it's referred to. Let's take a look at one of those messages. Now I have it in single shot mode again. Now I already have my knobs on my keyboard set to a few different controller numbers. So I'm gonna go ahead and turn one of the knobs here. So this time we'll be able to decode this a little bit easier, because what I did is I have this knob set to MIDI control change 0, and then I had it send out a 0 also. So that's going to be very easy to decode here. So we have a start bit, which is a logic 0. So that goes down, and then that stays low because we've sent all zeros. So it stays low and then ends with that stop bit. The second word or byte also goes low, and then we send it 8 zeros, and then also has the stop bit, which in this case is high on our screen here. Sometimes I know that gets a little confusing, but the MIDI CC numbers on this keyboard, they're only sending out the information for the last 2 bytes. It's not, as you see here, it's only 2 bytes. It's not 3, or 2 words, not 3. So anyway, I'm going to put this back into single shot mode, and now we'll send it the same controller number, but the value is going to increase. So now we have still the same controller number, so that's why it's all zeros. But now you can see we have all zeros and a 1. But remember, we send out the least significant bit first, so this 1 is actually right here. So we have a start bit that goes down, which is basically a 0. We have our 1, which is this right here, goes to all zeros again. And then right here we have our stop bit, which in this case is basically high. Now then, you can imagine maybe what's going to happen if we increase this again. So now, once again, we still have all zeros. Now we have a 0 and a 1 on the second byte. So it goes down for the start bit, comes up for, actually, pardon me, it goes down for the start bit. It also stays down because of the first 0. Comes up for the second bit is a high, is a 1, and then it stays low. If we do this again, we'll be able to see same exact thing. And so basically this is just counting in binary. That's all we're doing here. So if you know how to do that, or you want to look that up online on counting in binary, that's all this is doing. So it's really easy to decode. Once again, this first message still hasn't changed. It's all zeros, so down for the start, all zeros, up for the stop. Second byte goes, the second word goes down for the start. We send out 2 1s, so that's why it's high for this period. It goes down for the rest of the message, and then ends with a high stop bit. Now then, that's all on controller number 0. Go back into single, and we'll do the next one. So, and in fact, let me do that one more time. So now we have controller number 1, which is usually the modulation wheel. So it's the exact same thing. We are sending out controller number 1. So there's our start bit, the 1, all the zeros, the stop bit. Here we send out the number 0, so that's why it's down this whole time. So right here next to the box, it goes down, it stays down for the 8 zeros, and then at the end of the box it comes up for our stop bit. If we go back and clear that and send out a number 1, you can see it's exactly as earlier. So we have controller number 1 and value number 1. We'll do it again and send out a 2, which you can see when you count in binary is 1 0. So that's why it's, or pardon me, a 0 1 if you're coming from this side. So the second word, start bit down, stays down for the first 0, comes back up for the 1, stays down for 0, finishes high with the stop bit. And as you can imagine, we'll send it a 3, controller number 1, sending out a 3 in binary. So once again, it's just counting in binary. And for MIDI CC data and even the MIDI note data, that's all we're really doing. But what's nice on the oscilloscope here is we can see the actual highs and lows of our message. As I mentioned before, you may be wanting to view this information on the oscilloscope because you're trying to debug something. Maybe it's your baud rate. If you don't have a way to automatically tell the timing of this data, we can use the oscilloscope to do that. So I'm going to turn on the cursors. So we'll just go here. We're going to go to manual mode. I'm going to move this down. And then I'm actually going to go move the decoded information here too. So I'll move that down. And that'll just allow us to see the messages a little bit easier in regards to where our cursors are. All right, so here is this yellow line right here, and that was our start bit. So I'm going to move the cursor. I'm going to move the cursor right to the beginning of that. Now I'm going to switch over to the second cursor. We're going to go to the end of that. Now then, if we remember on our web page that we looked at earlier, we said that one word, 10-bit word, that is, at the 31.250 kilobits per second would equal out to a length of 320 microseconds. And as you can see, that's exactly what we have here. So from the start to the end is going to be 320 microseconds. Now, because once again we said we were starting with the least significant byte first, we have our start bit here. We have our 4 zeros. We have right here at this yellow, the 1, 2 more zeros. We end with the 1 and the stop bit. So we can actually measure how long a single bit, like this one right here, had the length of that. And if you do your math, you might already know if we've got 10 bits in this word at 320 microseconds, you might be able to, hopefully in your head, be able to calculate it, but we'll just double check right here. So we'll get that there, go over to cursor A and move it to a single bit of information. And you can see right here, 32 microseconds for a single bit of information. And then that can help you, you know, if you were troubleshooting, it can help you decode things to make sure you're at the right baud and that you're sending out the correct length of your bits and information. Now this has just been a quick primer on how to view MIDI serial data on an oscilloscope. However, I think it's a good starting point for any other types of MIDI messages, even more complex ones that you wish to view on your oscilloscope. I've put links to all of the tools and resources that I used in this video in the description. And as always, if you enjoyed this video and found it helpful, please give it a thumbs up and don't forget to subscribe to the channel. Thanks for watching.